Right, so that's part A. That was the first question I wanted to have a look at closely. I'm going to skip this integral because it was done pretty well. Let's have a look at part C, which is a mechanics question. A particle moves in a straight line such that x double dot, our acceleration, is equal to this particular exponential function they give us, where x is the displacement in centimeters at time t seconds. They give you an initial condition, namely that the particle's at the origin, so there is a, let's use this color, there's a displacement piece of information, and then they also say it's moving with a velocity of 2 centimeters per second, so that's important too. Determine an equation for velocity in terms of displacement. Okay, so v in terms of x. Right, let's have a go at this. So this is part C. Let's just start a new page. Here we go, part C. Now, if I just start with this equation of motion that's been handed to me, which is x double dot equals minus 2 e to the minus x. Knowing that I need to head towards an equation for v in terms of x, I have two very valid choices for how I'm going to express acceleration that will allow me to integrate most effectively from acceleration up into velocity. And honestly, they both work just fine, so I'm going to show you both. Let's go with method 1. Let's use the d half v squared on dx version. So if I just choose, don't know why my e is so messy and that's bothering me, there we go. If we just choose to define that left hand side as d on dx of half v squared, that's going to be equal to minus 2e to the minus x. What are we going to do here? Well, I'll double everything, so I just have v squared, so that's going to give me d on dx of v squared is equal to negative 4 out the front, e to the negative x, and I'm ready at this point to just integrate with respect to x, which leaves me with that v squared on the left hand side. There's no reason for us to worry about putting that constant coefficient inside the integral, and that just leaves me with e to the negative x dx. Actually, I take that back. Having that minus sign is kind of handy because, of course, that's going to be my inside derivative of my inside function up there. So this is looking really good, right? When I do my integration, I'm just going to get on the right-hand side, the 4 is hanging out there, and then it's just going to be e to the minus x plus a constant, like so. Now, I can use the initial conditions that I've been provided to work out what this constant is. So I can say, being that I've got an x value here and a v over here, the initial condition, it's, my question paper has gone away, here we go. Our initial condition, you might think like, oh, where do I put t equals 0? Because it's initially, right? But what I've got here is independent of time. All I need to say is, at the same moment, I'm at the origin, which is, whoopsie daisy, there we go. Oh, where's my cursor gone? It's absolutely disappeared. There we go. Huh. Funny. It's playing up. Yeah, my cursor's here. And it's not there. Weird. Doesn't matter. I'm just going to keep on going. I'm at the origin. There we go. And as already highlighted before, I have a v equals 2. Right? So I can substitute that in right here. I can say when x equals 0, v equals 2. So therefore, I can put this in and evaluate c. So what I'm going to get is, on the left-hand side, 2 squared is 4. You're going to get 4 times e to the 0 here. And remembering that e to the power of 0 is 1, I can subtract 4 from both sides and get the fact that that constant is equal to 0. So therefore, what have I got here? V squared is equal to 4e to the negative x. We didn't want velocity squared as a function of x, we wanted velocity. So therefore I'm going to take the square root of both sides. That leaves me with, careful here, plus or minus, I'm taking the square root of 4, which gives me the 2. And then just using index laws, I'll have e to the negative x on 2 here. Okay. Now, at this point here, I'm going to need to deal with the fact that I've got a plus or minus, because like, which one is it? Which one has to be the function of velocity? Is it the plus or is it the minus? What information do I have access to? Now, again, if you just go back to the fact that v equals 2 when x equals 0, that's a positive velocity, right? So therefore, if I put in x equals 0 back into here, you can see if the negative case were true, I'd get v equals negative 2 times e to the 0. That's negative 2, but I already know that's not the case, right? So I need to appeal to that again. I can say, but v is positive when x equals 0. So therefore that allows me to exclude the negative case. So I can say therefore v is equal to 2e to the negative x on 2. And it was no dice if you just kind of, left out this statement here and just chose the positive one, because if you didn't have a reason for it, it was arbitrary. It didn't show understanding that you knew why to eliminate the negative option. Okay, so there's your velocity function as requested. Now, I promised earlier that I would show what it would look like if you didn't use this method. I didn't mention it earlier, but you can think about the fact that there's one other form for acceleration that makes it easy to get velocity as a function of x, and that is of course v dv on dx. So let's use that instead and see what happens. If you go v dv on dx and let that equal to minus 2e to the minus x, what's going to happen? Well, you can see here, if I integrate both sides, I don't know why that x is so messy. If I integrate both sides with respect to x, what do we get? Well, I'm going to have my integral of v dv over on the left, and then I'm going to have, I'll do the same thing that I did before. I'll pull out that 2, but I'll leave the minus sign in here to go with that negative x dx. So you can see what I've done. I'm getting that, let's put it in blue. This v dv up here has remained on the left-hand side, and this dx over here is what has sort of combined with the e to the negative x on the right-hand side to give me a reasonable integral, okay? Now, at this point, to make it easier for me, there's an additional thing that I can do. Like I've already shown you can evaluate the constant and so on, but because I've recognize the fact that I'm going to need to use the initial condition over here to evaluate that constant, I can actually do this in this line when I introduce the integral, right? What I can do is I can say, let's consider that initial condition and then some arbitrary velocity and displacement, right? So when I'm at t equals 0, where am I? And the answer is I am at the origin. X equals 0. So that goes with the x boundaries over here on the right hand side. By the same token, initially, what velocity do I have? And the answer is v was given as 2, right? So you can see how these correspond to each other. And then I can just say, well, let's just compare some other arbitrary x and arbitrary v that pair up. And this will be enough because they're now both definite integrals to not have to worry about the constant at all, right? So I just need to evaluate these. Let's have a go. I'm going to get v squared on 2 from 2 to v, and then over here I've got 2 outside of e to the negative x from 0 to x. So far so good, definite integrals. Let's do our evaluation. Substituting v into v, I know that's a sneaky thing, but you just get v squared on 2. When you put 2 in, our lower boundary, you're going to get 2 squared on 2. So there it goes in the v. Let's deal with that in a second after doing the right-hand side. I've got the 2 there. Substituting x into x, you're going to get e to the negative x. And then I'm subtracting 2 because that 2 right there multiplies by everything on the inside. That's e to the 0, which of course I know is 1. So what am I getting here? I am going to multiply everything through by 2 to get that v squared on its easier to make the subject. So I'll get v squared minus 4 is equal to what I got on the right hand side. So multiplied by 2, that gives me 4e to the minus x, which I hope looks familiar, minus 4 because that was just going to be 2 and I just doubled it. And then I'm adding 4 to both sides. That gives me v squared equals 4e to the negative x. And at this point, where am I? I'm right here. So everything else just kind of carries on as before. So whether used d on dx half v squared or v dv on dx, they both landed you there. Though you do see if you can handle this sort of definite integral sort of somersault, this sort of calculus trick, I think the working does end up a little bit more sort of efficient because you're not having to do a secondary working out of the constant, even though that's very easy.